21-1 is about magnets and magnetic fields. This is the beginning of magnetism. Okay, the beginning of magnetism. It's very theoretical, this section. There's no math in this section, okay? All theoretical. So we're going to do three things. We're going to look at predicting whether magnets attract or repel. Still on the test, yeah. Test not till next week, so obviously. The test is primarily chapter 20, and what we do in chapter 21 today and tomorrow. I think 19.3 might also be on the test, unless that was on last chapter. We'll take a look when we get to that day. Next, discuss the magnetic field around a permanent magnet, and then the Earth's magnetic field. All right? First, poles. In terms of magnets, poles are what are called the ends of magnets. It's like the positive and negative terminal on a battery. Okay, like a AAA battery, think of it that way. It's a positive and negative pole. I'm going to read some stuff to you. Okay, I want you to write down what you think is important. Again, highly theoretically here. First, the name north or south, okay, is derived from a magnet's behavior on Earth. That's where it actually comes from. Now, if the magnet were allowed to rotate freely, the north end of the magnet would rotate and face the north pole of the Earth. Again, if you had the Earth right here, and here's the Earth's North Pole and South Pole. If I were to put a magnet right here, randomly on the surface of the Earth, and I were to have the North Pole of the magnet, it would face the North Pole of the Earth.
That's how compasses work, right?
Yes, that's exactly right. That's how a compass works. It's magnetically charged. Okay? So that's how that works. It faces the North Pole of the Earth. The North Pole of the Earth. I'll talk more about Earth in a minute. Next. Like poles repel and opposites attract. Just like, please, just like, yeah, electrical charges. Thank you, James. Electricity. Likes repel and opposites attract. Third, magnetic poles themselves cannot be isolated. They cannot be isolated. They always come in pairs.
Wait, would you say can be?
Okay, they always come in pairs.
Wait, would you say can be isolated?
The magnetic poles. And we'll talk more about that in 21-2. Okay, but magnetic poles cannot be isolated. All right, let's go to this. Permanent magnet is defined. Aaron, why don't you read it for us, nice and loud.
A permanent magnet, an object made from a material that creates its own magnetic field.
Okay, so it's made from a material like what? What's a material that creates its own magnetic field? There's one that's always used, that's always talked about.
Copper?
Not copper.
Lodestone.
Say again?
I know lodestone, but
Lodestone?
yeah, it's what they originally used as compasses. They float a piece of this in water, and that was the original compass.
Okay, I never heard of that, but there's one that's like very obvious that you always talk about. It's what an object is called ferromagnetic. What is it?
Iron.
Yeah, you know your Latin well?
Yeah.
Ferromagnetic. What's the element for iron on the periodic table?
Fe.
Fe. Ferromagnetic, Fe. Okay? Iron. So, first of all, permanent magnet. So, some materials can be made into permanent magnets by what's called induction. Okay? So, if you bring another magnet near it for a long enough time, it can become magnetic. And these materials have to be what's called ferromagnetic. A material that is ferro, F-E-R-R-O, it's a terrible R, ferromagnetic.
Yeah, I don't understand that.
A material that is ferromagnetic that contains iron can be made into a magnet even though it is not, because of a magnetic field that has been induced on it. Just like induction with electric fields. Remember how you can induce a charge by bringing it near the object? It causes the poles to kind of switch. It's the same thing here. Materials that respond to magnetic fields, that respond easily, are considered to be what are called soft magnetic or soft materials. So an object that can be easily magnetized or made into a magnet would be called magnetically soft. But they don't hold the magnetism easily. It's like when you heat something up. Everybody knows the baked potato. Who's made a baked potato before? Or who's eaten a baked potato before? All right. When you make a baked potato, at least, you have to put it in for like an hour and a half in the oven at 400 degrees. It's a long time because the specific heat capacity, C, of a potato is very high. So it takes a lot of heat to heat it up, but it retains that heat for a long time. A hot potato does not cool down for a long time. So you would say that's like a magnetically hard object. Okay, a magnetically hard object, it takes a lot to make it magnetic, but it'll hold that magnetic charge for a long time. Something that's magnetically soft, it's very easy to make it into a magnet, but the minute the magnetic field is removed from it, it loses its magnetism very easily. Okay? Everything can respond to a magnetic field, but some things would literally not change over the longest period of time. It would take eons and eons for it to become magnetic, whereas things that are ferromagnetic can easily become magnetic. Yes?
What about, so like why if there are substances that can be made magnetic, then why are there substances that are always magnetic? Like, why are there some that are, like, just by virtue of existing?
They're naturally occurring magnets. They're not induced.
Right, exactly. Why can some be induced while some are?
Because the ones that are naturally occurring, it's the bonds, the polarity in the bonds that are causing it. So you know how you talk about polarity for like H2O bonds?
Mm-hmm.
Your hydrogen bond is a polar bond. There's a positive and negative end to it. So certain materials have polar bonds. And depending on the arrangement of the molecules, we're going to look more of this in the next section, but you look at on a microscopic level the poles. And if there are poles within each of those bonds and they line up accordingly, it becomes magnetic. If you look at magnetic domain theory, you'll learn more about it. We'll see that in 21-2. I don't want to answer it just yet, though, just because we're going to get to that, James, okay? Give me another second, okay? A magnetic field. Tori, answer that for us.
A region in which a magnetic force can be felt.
So a magnetic force. A force can be felt where there is a field. So this is a magnet right here. There's a north pole and there's a south pole. The field is drawn from the north pole to the south pole. Take a look. When you bring a compass, the north pole on the compass, the red is north, points toward the south pole because opposites attract. Very good, Gio. Opposites attract. So notice that was the Earth. And be careful, and that's why I said I go into that. For the Earth, the north pole of the compass goes toward the north pole of the Earth. But the north pole of the Earth is not really the magnetic north pole of the Earth. They're reversed. And I'll explain that in a minute. But for a regular magnet, if you had a magnet and you brought a compass toward it, the north pole of the compass would point toward the south pole of the magnet. Okay? Because opposites attract. That's exactly right. Now, you could also say that a compass would always point in the direction of the field lines. Look at the compass. Look at the North Pole. Isn't it right along the field lines on this? Okay, these field lines are just like the electrical field lines. If the field lines are closer, it's a what magnet? Just like electrical. It's a stronger magnet. Remember, more dense field lines closer together, relatively speaking. We don't have a number for it. But more field lines, the stronger it is. They're like contours. Give me 1 second. Other things I want to discuss. Hold on, let me just see if there's anything else. Alright, so let's talk about the Earth, right? The North Pole of the Earth, okay, is really called the geographic North Pole. So let's write that down. The geographic North Pole. And that's what we just drew a moment ago. So I'm going to draw this diagram here. Here's the Earth, North and South Pole. Here's the compass with its north end facing the North Pole. This is the geographic North. This is the geographic South. But the North geographic pole is really called magnetic South. And this is really called magnetic North.
Who screwed this
Okay.
up when they were writing it?
Nobody screwed it up. Nobody screwed it up. It was just the idea that came about first, and then they switched the idea or the notion. One thing to notice, though, is that the poles on a planet can switch. They can switch, and it has happened in the past. There is more history about that. Give me a sec. I'm going to talk about how it works. Okay? So the Earth's magnetic field is not really known as to why it exists. Believe it or not, it's still theorized, which is pretty crazy to think about. We know so much about physics and science, but the Earth's magnetic field is not really due to iron. Okay? What its theory is that it's due to convective currents in the Earth's core. So, in the core of the Earth, there's this fluid, this plasma, right, moving around. There's that molten rock that's moving around in the core. It's heated up. Convection is the movement of a fluid. The movement of that fluid, and it happens to be polar or polarized or charged, that movement of fluid is what is considered to be causing the magnetic field. Give me one more minute. Okay, magnetic field. The strength, these are fun facts that come up on your test. The strength of a planet's magnetic field is directly related, or thought to be, directly related to its rate of rotation. So a planet that rotates faster would have a stronger magnetic field. Stronger magnetic field. Last but not least, this is so interesting. You should really listen to this. Bacteria on the Earth use the magnetic field of the Earth to know where to move. There are bacteria that can't see. There are a lot of bacteria, amoeba, that don't have eyes. And they actually know to move toward the surface or away from the surface based on the magnetic pull. Because their bodies are magnetic. So they can feel or sense the magnetism of the Earth and use that sense of pull or push to know where the surface is or where the core is. To know which way to travel. Okay?
Isn't that like moss?
Naturally occurring magnetic bacteria. I don't know. Are moths?
Does it?
Moths are attracted to like light and stuff. Yeah.
Yeah, isn't it like the Mars goes away from
Birds, when they
civilization?
navigate with
Because
us,
that's
it's like
one
magnetic
SpongeBob
Homework. Write it down.
where they're lost, and
To be
then
on the moon.
it's like, oh, the moss is facing that way, and that's towards the position, and they were wrong, and it's faces away from the
It's probably some sort of extension of that.
I'm
Yeah.
guessing like maybe moss